Hi, welcome to the class. Today we'll start a new chapter. The name of the chapter is atoms. And in atom, the very first topic which we will be doing is Rutherford's alpha particle scattering experiment. Now, what is this alpha particle? Let me just first clarify on this. This alpha particle is basically a positively charged particle, and this positively charged particle is nothing but a helium nucleus. So this is 2He4. Now guys, you should recall that this 2 is what we call the atomic number and this 4 is what we call the mass number. So atomic number has a denotation of Z, which is atomic number, and atomic number is always equal to the number of protons, right? And then atomic number is equal to number of protons. And then you have A, that is this one. So basically the representation of a nucleus, which we will be doing in the upcoming chapter as well. Representation of a nucleus is always done like this, Z, X, A. So Z is this, X is the nucleus, like we have helium nucleus here, which is the alpha particle. Alpha particle is nothing but helium nucleus. And then you have this A, which is the mass number. So mass number is equal to the number of protons plus the number of neutrons. So A is equal to number of protons plus number of neutrons. Right? So this is the first thing which we have to discuss about is the Rutherford alpha particle scattering experiment. Alpha particle means helium nucleus, 2He4. This is Z, which is atomic number of protons. A, which is this is the representation of a nucleus. A is what we call number of protons plus number of neutrons. Now here is the setup. There is a radioactive source which will emit this alpha particle. These are the lead blocks which are put. Why these lead blocks are put? The reason is because when you put these lead blocks, the possibility of this radioactive particle traveling straight and hitting a target is increased. Otherwise they may deflect here and there. So these lead blocks are what we call the collimators. So they keep it on the track. And the Rutherford did the experiment with the gold foil. And the atomic number for gold foil is Z is equal to 79. Gold foil. Why he chose gold foil? The reason is that when you start slicing the gold foil, you could slice it to the thickest of the layer. That's why. And once this happens, then some of the particles will deflect here and there. So we have the particle detector, which detects the particle. So what we are supposed to understand in this experiment? So basically what we are supposed to understand in this experiment is first of all the observations which he made, right? So the first observation which he made was this, that the most of the alpha particles passed through the thin foil undeviated. It means they did not deflect here and there, but they went straight, like most of the particles, right? Then some of the particles, this is the second observation, that some of the particles deviated to great extent. So some of the particles came straight and then they deviated to a great extent. And the third one was that very few particles rebounded back. They rebounded back and traveled through means they deviated through the same path. So these were the three observations. What were the three observations? Just to do the review. First one was that most of the alpha particles passed through the thin foil undeviated. Second, some of the alpha particles deviated to a great extent. And the third, that some of the particles, some of them rebounded back. Now what would be your explanation? Now observations we have made, but what would you conclude after getting these observations? So what was concluded after getting these observations was, the very first thing is that the particles going straight represents that there was nothing in their way to deflect them, and therefore the most of the space. So first conclusion was that most of the space inside the atom is empty. So that's why they were able to go straight. Suppose this is the atom, so most of the space inside the atom was empty and they could go straight without deviating here and there. So this was the first explanation for the first part. Now the second part, since alpha particles are positively charged particles and alpha particles are very heavy particles, right? They are heavy particles, they are not light particles. So when they are heavy particles, what happens is, in order to deflect these positive charge particles and the heavy particles, what we need is a greater force. We need a greater force to deflect them backwards. And how do we get that force? We get that, and deflection will take place only when we have a positive charge against them, because they are positively charged, and in order for them to deflect back, you need a positive charge there. So what Rutherford concluded, that inside the atom there is somewhere there is this positive charge concentrated inside the atom, right? So by that time he did not gave this word or coined the term nucleus, but he told that okay, inside this somewhere inside the atom you have the positive charge which is concentrated at a place, and obviously the mass also, because this is a very heavy particle. Alpha particle is a very heavy particle, positive particle, and therefore you cannot deflect it with a small amount of force. So therefore the total mass of the atom, or the total positive charge of the atom, is concentrated at a point, and we know that what that point is known as, of course that is known as nucleus. So that's why these particles were either getting deviated with a greater extent or were getting deviated backwards. So that is how this works, right? So these were the important three observations and their conclusions which were made in this experiment. Of course I'll be dropping the notes in the link of this video, so you could easily find these things there, right? Now the biggest question to ask is this, that when this alpha particle went closer to this atom, obviously before deflecting, how much closer it went? How much close it went? So that is what we call the distance of closest approach. Distance of closest approach. Now the distance of closest approach we have to figure out, because that is quite evident that it will not go very close to each other, and they will not make any physical interaction, because this there is a force of repulsion, and because of that repulsion it will deviate well before at some distance itself. So we want to find out how much close it will go. So that is what we call distance of closest approach. So suppose this is the atom and here it is positively concentrated thing, and you know that inside we know that actually inside this atom we have nucleus, and remember guys, as I told you, inside the nucleus we have protons, and Z is atomic number which represents the number of protons. Now Z is equals to number of protons. E is what? Charge of an electron, but the same charge is possessed by the proton as well. So this is charge of proton. So if you have Z number of protons and E is the charge of one proton, what will be the total charge inside this nucleus? Z. So remember that the Z is the charge of nucleus. And what is the charge of electron? E. The same as the charge of proton. Electron is revolving outside this thing. Now you see, when it approaches closely, well before turning, its kinetic energy will become zero. When it will turn, when its kinetic energy will become zero, only then it will turn back. So how much kinetic energy? Okay, and when the kinetic energy becomes zero, it will be converted into something known as potential energy. So when it comes and stops here, kinetic energy becomes zero, but where does this energy go? This energy converted into potential energy, and therefore kinetic energy is equals to potential energy. We all know that this will be half mv square. where mass of the alpha particle and velocity of the alpha particle. But what will happen to this potential energy? Now guys, I am explaining one very important thing here, which I will be using again and again, and I want you people to pay attention to this part. As we all know that potential is equals to work done per unit charge. Now work done is equals to potential into charge. Now guys, tell me, if there is no nucleus, do we have to do any kind of work to send the alpha particle towards the nucleus? Answer is no. Because if it is not reflecting, deflecting, okay, there is no force of repulsion, you will do work against which force? Because there is no force, like gravity. If there is no gravity, if you want to lift up a marker like this, if you want to lift up the marker from the ground and there is no gravity, against which force you will do work? And if you don't do work against any force, then there will be no potential energy in the marker. Similarly is the case for this. If there is no nucleus, so alpha particle will go straight because there is no force of repulsion, and then we need not to do any amount of work. So if this potential is 0, work done will be 0, and if work done is 0, then the potential energy will be 0. Now potential, we are studying that potential due to a single charge is 1 upon 4 pi epsilon naught q upon r. This is the potential due to a single charge. Now whose potential? Alpha particle is traveling in the potential of, what do you call it? Nucleus. So 1 upon 4 pi epsilon naught Ze, which is the charge of the nucleus, upon r. This is the distance which I am assuming that is the distance of closest approach. So let me mark it as r into who is coming there? Who is coming in the vicinity of this nucleus? Obviously alpha particle. And how much Z, how many Z this alpha particle has? It has 2Z. Why Z is equals to 2? Because 2 protons are there. And 1 proton has a charge of E. And then 2 protons will have a charge of 2E. So this amount of work done will become the potential energy. And therefore, instead of this potential energy, I am writing this expression because whatever amount of work done we do against this force of repulsion, it will become the potential energy. And therefore, it will be Z 2Z square. 2Z square upon 4 pi epsilon naught R. Now R naught will be what? 4Z square upon 4 pi epsilon naught mv square. So this will be, I am not cancelling out these two because I know the value of 1 upon 4 pi epsilon naught. So that is how it could work out. So this is the least distance. This is the distance of closest approach. It means if you use this formula and if you know other details, you could easily calculate that how much closer it will go to the nucleus, this alpha particle, right? So I hope this part was clear to you. Thank you so much.